We're going to derive here the simplest finite difference representation for the heat or diffusion equation we do have here. And this is called the explicit forward time centered space method for the diffusion equation. So here we have like two different terms. One is the partial derivative of u with respect to time, and the other is the second order derivative of u with respect to space. So for the partial derivative of u with respect to time, in order to get a finite difference representation for this one, as we did for the advection equation, we just need the Taylor expansion in order to get an approximation for the u function evaluated at position x and time t plus delta t, which is this one. And from here, we can actually just clear find a different representation of the partial of u with respect to time, just in terms of the values of the u functions at two different times. And just clearing from here, we get that expression. And if we apply that one at around just position n and time j, this is the finite difference representation that we do have, or that, as you can see here, the error is of the order of delta t, the error of each step, of course. Then we are going to do now the finite difference representation, in this case for the partial derivative of u with respect to second partial derivative of u with respect to x. Okay, in this case we just we need more than one Taylor expansion in order to get that, because yes, in order to appear the second order derivative of u with respect to s, you need to go in the Taylor expansion up to second order. And if you go to the second order, you also have in the middle the linear term, which is proportional to the partial derivative of u with respect to s, x, that, and you want to get rid of that in order to have a finite different representation of this one, second order derivative, just in terms of the values of the u function. That's why in this case we are going to consider just two Taylor expansions, the one we do have here. One Taylor expansion in order to have an approximation of the u function at position x plus delta x and time t, and another Taylor expansion to get an approximation of the u function at position x minus delta x and time t. So these are the two Taylor expansions. As you can see, they are the same actually. The only difference is the sign here of the linear term, because one is forward, so in this case delta x is positive, and the other one is backward, so you have delta x is negative. So here you have that linear term is going to be negative, and we are going to cut it up to second order, where we already have this second order derivative of u with respect to x. So as we said before, we want to get rid of this linear term. That's why we are considering these two, and as you can see here, both have just opposite linear terms. So you just sum these two Taylor expansions, and summing these two Taylor expansions, this is the result of what we do have, where we are keeping this second order derivative of u with respect to x. And what we have to do now is just clear from this expression the finite difference representation for the partial derivative of u with for the second order derivative of u with respect to x. And doing that, this is what we have. Okay, so now the only remaining thing is just get this expression and apply that around position defined by index n and time j. And doing that, that's the finite difference representation that we do have. As you can see, it is connecting like three values of the u function evaluated at three different positions of x, and the order of the error of this approximation in each step is the square of on delta x. So collecting everything and substituting this partial derivative of u with respect to time with this finite difference approximation, and the same with the second order derivative of u with respect to x. So the expression that we do have is the following, is this one. Therefore, this is the final difference representation that we do have, and the order of the error that we have is delta t and the square of delta x. That's interesting to have also like a graphical picture of this final difference representation. So here, as we can see, the dashed line represents like the points connected by the time derivative, and you can see the time derivative is connecting points located at nj and nj plus 1. And actually this is the value that we actually don't know and we want to calculate, and we are going to do that just based on the values of the u functions located at the previous time step. And on the other hand, you have that the partial derivative of u with respect to the second partial derivative of u with respect to x, it's connecting these 3 points that are represented here by this solid line. The black dots again here represent somehow the values that we already know, and the method, the philosophy of the method is once we know these values, the idea is to get using that final difference representation to get the value of the u function at next time step. So the only remaining thing in order to get the final difference representation that we want to apply in order to solve the equation is to clear from this expression this the value of u at time j plus 1. And when we are doing that, this is actually the expression that we do have. And as it happens for the advection equation, okay, here we have to apply that for n going from 1 to nx minus 1, where nx in this case will be the number of space steps. And also the alpha parameter arising in this equation here in order to simplify the expression is basically d, the conductivity, times delta t over delta x squared. So again, each time step, these are the equations that we have to actually apply. Actually, these are like nx minus 1 equations that we do have to apply in order to get the values of the u function at all the points, all the x points, all the n points, and we have to do that for each time step. So basically here we have derived the simplest final difference representation. The simplest in the sense that this is the lower, the lowest order of the error that we can consider. So this is the simplest final difference representation we can have for the heat or the diffusion equation.